right, it is the 15-minute mark to the hour, so we're going to go ahead and get started. Those of you who are here, welcome to day 3 of the Earth Science Applications Week. We are on track 2. We're going to be going through some flash talks. Let me cover some of the, well, here's the welcome. I'm glad y'all could join us today. And before we begin, we're going to go over some logistics and some meeting etiquette. We do request that you keep yourself muted and your video off if you're not presenting, just to save on bandwidth. If you have questions for the speaker, feel free to write them in the chat. After every about 3 or so flash talks, we'll have a Q&A portion, so you can save your questions for then, or you can type them in the chat and we can address them once we hit that Q&A portion. And these sessions will be recorded, so if you want to go back and look at them, feel free to do so. And we're going to go ahead and get started. Here's a little bit of the agenda. So we're going to have flash talks from 2:15 until 3:30, and then we'll hear about the capacity building program. And then we're going to go back to flash talks to conclude the track. And so we're going to begin first with the Powder River Basin Water Resources team. And we're going to start with Catherine Busick and Carissa Courtney. And they're going to be covering the mapping of the Russian olive in the Powder River Basin to inform invasive species management. And y'all can go ahead and kick it off.
Awesome, thanks. Yeah, so today presenting will be me, Carissa Courtney, and Catherine, and we'll be representing the Powder River Basin team. Next slide. So as the title alludes, the invasive species of concern was the Russian olive. It is a deciduous woody tree/shrub native to Europe and Asia, and it was introduced to the US in the 1800s as a windbreak and a ornamental. It often outcompetes native vegetation, is dispersed by animal vectors and short-term flooding, and is a nitrogen fixer. So this species is of concern in many areas of the US, but especially in the Powder River Basin, which was our study area. It's located in Wyoming and Montana and spans 7 different counties. And the Powder River is a critical water resource. And so invasive Russian olive outcompeting and decreasing biodiversity is of a special concern. So it can also impact local hydrology and potentially change the stream channel shape. Next slide. So for our study, we performed a random forest model as a feasibility study to see if we could successfully detect Russian olive from satellite imagery. So to do this, we first collected ocular samples using NAPE visible imagery from 2019 and combined that with field data collected from our partners from the University of Northern Colorado. So we used this to train our model, and then our model operated off of Sentinel-2 and Landsat 8 imagery, and we also incorporated SRTM elevation data as a topographical variable, as well as a LiDAR canopy height model. So on the right, you can see our output for our Russian olive detection map, and we were successful in creating this, and Catherine will go more into some details on where you can see Russian olive on our maps.
So here we have 2 images. On the left is an image from NAPE imagery. This was what we used for our ocular sampling, but highlighted in the light blue boxes is an area where Russian olive is present. You can see Russian olive by its light sage color, and on the right is one of the is our results from our random forest model. So the yellows, greens represent areas where Russian olive was detected by our model, and you can see clearly that our model was successful in identifying this particular area where Russian olive is present. And I should note that the blues mean there's absence of Russian olive. So if you can do next slide, I think there's an animation. So here we have an example, left just visible imagery, right, our random forest model. Results, this is an area where our results maybe aren't performing as well, and I think we later got rid of some of these areas by omitting any value below our root mean squared error. But on the left, you can see that there is still a crop circle that is detecting an area where Russian olive is present when clearly there is no Russian olive in an area where there is crops. So that is one thing we've been fleshing out as we head into last week. Next slide. So some takeaways and importance. The current Russian olive research lacks the use of satellite data and remotely sensed data, so we helped bridge that gap. We were able to successfully model Russian olive within the Powder River Basin for our partners, and the model is built on a purely spectral detection map, so it's independent of any topographic variables, which makes it a strong model to use outside of just the Powder River Basin. So that's one thing that we're interested in maybe doing in the future, is seeing how this model performs outside of the Powder River Basin. Our results will help empower our partners and local stakeholders within the Powder River Basin to make informed decisions around Russian olive management. And our results will also support research that is currently going on and will continue to be going on out of the University of Northern Colorado regarding Russian olive invasion and other invasive species in the Powder River Basin. And that's all we have. Next slide is our acknowledgement. So thank you. And I guess we'll save questions for later.
Wonderful, thank you. That was very interesting. Random forest modeling, and that's always a joy to do. So next we're going to have the Southwest Water Resources. We're going to have Rebecca Bernat and Kyle Polakis. Please tell me if I pronounced that wrong. Sorry about that. And they're going to be discussing monitoring surface water extents of remote stock ponds in the southwestern United States using Earth observation systems for enhanced water resources management.
Yeah, my name is Kyle Polikas, and this is my teammate here, Rebecca Burnett. We're here today on behalf of NASA Develop Idaho and the Idaho node of the Southwest Water Resources team. And today we'll be presenting on our project of using Earth observations to monitor surface water extent in remote stock ponds. Next slide, please.
Ranchers and land managers rely on stock ponds to provide water for their cattle and wildlife. On the map on the left, you can see several hundreds of identified stock ponds. In blue are ponds of the Kaibab National Forest. Half of them are located around the Grand Canyon. And in purple are ponds of the Barty Bar Ranch. Almost all of the ponds are located in Coconino County, Arizona. If you've ever been to the Southwest, you know how vast the landscape is. And so ranchers and land managers often have to drive for hours just to check on the water volume in their ponds. So in light of changing climate regimes and years of drought in Arizona, ranchers and land managers needed to innovate with sustainable water management strategies. Next, please. So that's when we came in. We processed satellite imagery from Landsat 8 mission. The U.S. Forest Service and the Barty Bar Ranch provided stock pond locations. After delineating the stock ponds, we applied a cloud masking algorithm in Google Earth Engine in order to reduce the impact of cloud cover on our images. We then combined different water indices commonly used for identifying surface water bodies. And finally, we used a random forest classification algorithm to differentiate water pixels from non-water pixels on our images. Next, please.
So with our classified pixels, we created a tool called the Surface Water Identification and Forecasting Tool, or SWIFT for short. The Google Earth Engine graphical user interface allows ranchers and land managers to assess water conditions within each grazing allotment. We tested our results with an accuracy assessment. We used high-resolution imagery over 300 points to visually classified them as water or non-water on a particular day. In the figure on the right, you see the points used for validation, with yellow representing the non-water and blue representing water observations. We then used 80% of these points to train the classification model and tested its accuracy on the remaining 20% of points. The overall accuracy is 93% for the testing data. The kappa coefficient, which accounts for correct classifications by chance, is of 0.88, which is very good. In conclusion, SWIFT is able to detect water with a high accuracy. Next, please. SWIFT will be beneficial for ranchers and land managers because it reduces the substantial time and cost to monitor stock ponds in the field. SWIFT is meant to supplement field monitoring, not completely remove it. Sufficient water is critical to the livestock industry for maintaining quality of animal health. For example, cattle production is one of the 5 pillars of Arizona's economy. Ponds conditions are also key indicators of herd health. For example, the Arizona Department of Game and Fish may issue fewer permits for hunting times of scarcity. There are opportunities for SWIFT to be applied in fire management. It could identify areas with high water content for potential fires. SWIFT could also identify areas with high risk that needs to be grazed. Next, please.
We'd like to thank our project partners and collaborator, U.S. Forest Service, Arizona Department of Game and Fish, and Diablo Trust. Also would like to thank our science advisor, Keith Weber, and Dr. Sap Kim, and also, of course, our NASA fellow, Brandy Nisbet Wilcox. Thanks for your time and attention today.
Wonderful. Thank you guys so much. That is a very impressive overall accuracy and kappa. So next we're going to hear from the Bhutan Water Resources 3 team. This is the 3rd term for them. So I'm really excited to see what they've got. And we're going to hear from Yeshi Selden.
Hi, I am Misha Salden, representing Bhutan Water Resources 3 team. This term, we assessed forest disturbances and climate data in Bhutan to assist Himalayan Environmental Rhythm Observation and Evaluation System, also known as HEROES project. Next. The study area of the project is the country of Bhutan, located in the Himalayas between China and India. Hometown and How were specifically chosen as areas of interest because of a major bog beetle infestation that was detected in 2016. The study period for this project is from 2000 to 2018, mainly focusing on the months October 31st to May 31st, when there are lowest cloud formations. As for the community concerns, Bhutan has experienced increased warming with a decrease in the annual rainfall and snowfall over the past decade and is facing high risk from glacial lake outburst floods. Changes in agriculture patterns due to climate variability affect agriculture and forest productivity, which in turn impact national food and fiber security. Forest pests such as bark beetle infestation contribute to forest disturbances, resulting in tree mortality and increased action of felling. Next slide. Okay. Precipitation and temperature data were used from the previous term's result, where it was derived from CHIRPS and FLDAS data sets. Accompanying that, this term we used Landsat 5 TM, 7 ETM Plus, and 8 OLI for images, and ground data from our partner, the Ugin Wanchu Institute of Conservation and Environmental Research. The Landsat images consist of historical images of land cover, which were then incorporated with an algorithm called LandTrendR, developed by Dr. Kennedy on Google Earth Engine with Normalized Difference Vegetation Index, NDVI. After importing Landsat imagery into the algorithm on GEE, the team generated codes to create an application called Forest Disturbance Detection Toolbox, in short FDDT. As for the ground data, it was displayed in ArcGIS with a background of LandTrendR result to verify that there were indeed disturbances observed in the given location. Next. To provide an overview of how the app works, after we run the code, this is how our current app developed by the team looks like with its respective features. The date slider in the green box located on the right corner allows the user to select a year to display the result of the climatic variable, which you can see in the pink box, that is temperature and precipitation for that particular year. The years on the slider range from 2000 to 2018. The drop-down menu, which you can find on the top left corner in the blue box, displays the option to select land trend variables for 2 areas of interest. The land trend variables in our project are in regards to NDVI, and they are duration, magnitude, prevalence, rate, and year of detection for forest disturbances. The legend in the brown box provides a legend for each LT variable, but only for duration is displayed on the slide. So, for example, if we pick a variable from HA, let's say duration, the app zooms into the area of interest on the map and provides a histogram for duration as seen in the black box on the left. The image and the chart generated by the app can be exported by user to observe and analyze. Furthermore, all the charts can also be enlarged by clicking on the Enlarge button circled in red, which appears right next to the chart. Next slide. Okay. So in conclusion, using the Google Earth Engine land trend code acquired from the Landsat data, the team developed an app called FDDT that helps to assess forest changes in Bhutan for the focus districts from 2000 to 2018. With land trend we are looking at a minimum of 10 years to observe any significant changes. For the ground data, the geocoordinates for known disturbances were provided to us by UVCR. We then had those points mapped to see if there were any disturbance observed spatially. For magnitude, we mainly investigated how big the spike was and how often it occurred. Based on our finding, the magnitude remained relatively low and there was a sharp decline. The modeled output observed a longer duration for Ha when compared to Bhutan. The year 2000 saw some very big spikes, suggesting that there were a lot of disturbances then. The project's FDDT will be provided to our project partner to aid forest management efforts in Bhutan. Additional work is needed since there wasn't much quantitative validation of any of the presented products. Next slide. Lastly, we would like to thank the following individuals for their influence in our work. Thank you.
Wonderful. Thank you very much. I'm an assistant geoinformatics fellow, so I saw how the code kind of came into fruition, and it's really awesome to see it fully fleshed out. So now we're going to go into a Q&A session for about 7 or so minutes so we can get back on track, and we'll get started at the 40-minute mark again. So if y'all have any questions, feel free to raise your hand, or there might be something in the chat. Sorry, I have not checked personally. Oh, yeah, Rebecca.
Hi, I have a question for the Russian Olive team. So I was curious to know how you were able to distinguish images from this species from other vegetations. I think you mentioned like some ocular sampling in the chat. I don't know if it's related at all, but if you could, explain how you did that, that would be great. Thanks.
Yeah, I can speak a little on it, and Catherine can add because I'm sure I'll forget something. But Russian olive is easily seen from aerial imagery. It has a distinctly different color and texture than any of the other species in the area. There's mostly just tamarisk and cottonwood that are other trees that live in the same area, and they're a very different color. We had to make sure that we were looking at the correct season though, because the leaves do fall off of the trees. So we looked at spring to fall and omitted winter. Yeah, and when we ocularly sampled, we made sure it was during the seasons when we could see it.
Yeah, and we also had, so we definitely used the leaf color to our advantage, and we had field data that was collected, which was about 240 points, but that wasn't enough for the model to run successfully, so we collected 2,000 random points just to create some non-bias data points. and we were hoping that we'd get more samples, but we only found 5 points out of those 2,000 that had Russian olive in them. So then we went and collected about as many as we could, about 400 samples where there was purely Russian olive presence.
Okay, thanks.
That must have been a wonderful learning experience to figure out 5 of the points out of the 2,000.
Yeah.
We're only there. I have a question for the Bhutan team. I am curious, do you know why there was such great disturbance in the year 2000? Is there anything that, like any sort of event that might have indicated why that was the case?
So our app just it's like it just gives an overview of that there was a forest disturbances. So that is actually one of the future work that our partners might do, that they're going to investigate like what actually was the event that occurred. Like they did say that they noticed forest disturbances. So that's just an overview of how it could be anything, like there's a lot of forest fires or deforestation that might have happened. So we cannot pinpoint that. So, but it just says that there's a disturbances. So it's more of a concern for partners so that they could look into it.
That's interesting and definitely a great new potential project. I can see that being. I guess the joys of emceeing is that I can get all my questions answered. I have a question for the Southwest Water Resources team. So that kappa and overall accuracy was very impressive to me. I've not attained that doing when I did my thesis. I was not near that, but I did have quite a few more classes. So my question is, would you guys have recommended additional classes? Or all you were looking at was water and non-water. Do you think like maybe, I don't know, like more turbid water or less turbid water would have been, I don't know, more fruitful to the project itself? Would you have recommended anything? And if so, what?
Yeah, I can talk on that. And I think we really wanted to keep the classes fairly simple, of just really what our end users were looking at was, is there water in this pond? And more specifically, doing our time series and our analysis, we kind of wanted to get to the point of looking at, is the water increasing or decreasing, which is more important to them. And so a lot of the areas we're looking at were just these ponds in the middle of nowhere, with not a lot of vegetation around them. So we wanted just to keep it really simple and kind of keep that down.
I guess that's really useful in the desert when there's not as much wetlands, and there's kind of like a ton of aquatic vegetation present and it's more difficult to discern.
One of the big things we are concerned about is ponds with a high turbidity getting misclassified as non-water due to their kind of unique, different spectral pattern.
Yeah, I can definitely see that. And so is this water being used like for consumption, or is it being used for like crops? I don't think it would be crops. I don't think that would be a great area.
So that water, it's used for cattle. Like the ranchers, they have mainly, like beef. That's, like one of the big economy there in Arizona. So it's for animals. That's the only water that they have out there. And it's also useful for the wildlife, and for forest services or Arizona Game and Fish to keep track of where the wildlife can get water, because there's very limited rivers, and yes, and those ponds, they were, for most of them, artificially created. So there's no like connection also to the groundwater, so they won't fill it up, on their own. And there's also very limited precipitation in the area. So yeah, many constraints. out there.
Definitely sounds like a very important project to be a part of. And if nobody else has questions, we're gonna keep it going. Let me go ahead and go back to sharing my screen. Okay, and so now we're going to hear from the Coastal California Water Resources 2 project. This is the second term, and we're going to hear from Rachel Darling, Alex Gunnarsson, and Sophia Stonebrook.
Thanks, Alexa, and thank you everyone for joining us. So just to reiterate, we are the Coastal California Water Resources 2 team out of the JPL node, and my name's Rachel, and I'm here with my teammates Alex and Sophia. And today we'll be discussing how to utilize NASA Earth observations to detect and assess the impacts of estuarine breach events for improved coastal wetland monitoring and management. Next slide, please. So estuarine ecosystems are partially enclosed wetland ecosystems, meaning they aren't always subjected to full force wave dynamics, storms, and other external processes like that. So estuarine ecosystems are extremely important because they provide a really vital host of ecosystem services, such as breeding grounds and habitats for marine life, as well as water filtration, storm buffering, and many other services that provide us with, valuable things. And so additionally, estuary breach events are really important to note because they significantly impact water quality metrics like salinity, inundation, and turbidity, which impact the ecosystems inside and outside of the estuary. So with the value and the dynamic nature of these important ecosystems in mind, the primary aims of our project were to firstly assist our project partners in estuary marine protected area monitoring using remotely sensed imagery. So secondly, we wanted to refine our SEA tool, the California Estuary Assessment Tool that had been built upon in the previous term of our project. Next, we wanted to validate our tool with available data. So we used visual inspection of imagery, in situ water level data, and other estuary assessment tools to ensure the efficacy of our SEA tool. And lastly, we designed a GUI, a graphical user interface that links all the different functions of our SEA tool in a user-friendly interface and output. Next slide, please.
For our analysis, we focused on 5 sites along the California coast, but for this presentation, we're focusing on the Russian River estuary, which is located just north of San Francisco, California. There are 3 parts to our analysis. The first part is about the estuary mouth state, so meaning is it open or closed? In this case, open meaning that the water can flow freely from the river to the sea, or closed meaning that it's blocked by a sandbar and so it cannot pass through. Second part is inundation or water level within the interior of the estuary. And then the third part is looking at water quality metrics both within and outside of the estuary. So for mouth state, we used Sentinel-2 NDWI imagery in order to analyze whether or not the pixels were water or non-water. From there, we took the water pixels and we analyzed to see if they were connected to each other from inside and outside of the estuary. If they were connected, it would return 1 object, implying that the estuary is open. And if we got 2 objects, it would imply that the estuary was closed, as they were 2 separate objects. For inundation, we also used Sentinel-2 imagery again to calculate the normalized difference water index, NDWI, and we used Sentinel-1 CSAR imagery to complement that by seeing through clouds and to increase the temporal resolution. And then for our water quality, we used Landsat 8 OLI to generate temperature and Sentinel-2 MSI to generate turbidity. Next slide, please. As you can see from the results here, we have the Russian River again, with these images obtained from the month of February. If you look at the image on the left in the first section, the mouth state is open. And for an open mouth state, we would expect to see lower levels of inundation, cooler waters inside the estuary, and high levels of turbidity. Now, for this case, we actually saw inundation levels a little bit higher than we were expecting, but we need to keep in mind that this point at this time of year typically sees increased stream flow and increased precipitation. So those could be confounding factors. Additionally, for turbidity and for temperatures, we actually did see what we would expect with a large turbidity plume and cooler temperatures inside the estuary. Next slide, please.
So the final part of our project was to condense all of our 3 scripts into one tool, a graphical user interface, which will allow our end users to generate time series charts of the selected parameters that they would like to investigate.
It will allow users to investigate potential trends between the different parameters to increase their understanding of these complex ecosystems in hope of improving estuarine monitoring and management. Next slide, please. And we would just like to give a big thank you to all of our science advisors and partners who have helped us throughout this past 10 weeks. Thank you.
Wonderful. Thank you guys so much. That was very interesting. And next, we're going to hear from my node, the Arizona node, for the Highland Lakes Water Resources team. And we're going to hear from Addison Pletcher.
Thanks, Alexa. Like she said, my name's Addison Pletcher, and welcome to our discussion of algae events in Texas, specifically the use of remote sensing and machine learning to help identify these problems early on. This was a project done by myself and my teammates, Caitlin Hippis, Mark Radwin, Shiyu Chang, and Emma Hua at the NASA Develop Arizona node. Next slide, please. So our area of interest for this project was the Highland Lakes region of Texas, composed of a chain of reservoirs on the lower Colorado River near Austin. The area began experiencing harmful algae events only recently, resulting in many headlines like these. As we know, algae is not inherently bad and is a natural part of aquatic ecosystems, but prolific growth of this blue-green algae, or cyanobacteria, can lead to the production of harmful toxins. In this case, two neurotoxins called anatoxin A and dihydroanatoxin A. It's these that cause complications after consumption. Reports of canine deaths from toxic algae first occurred in Lady Bird Lake in 2019, and toxins were also found in Lake Travis and Redbud Isle earlier this summer. Next slide, please. Our goal was twofold. First, we wanted to create a near real-time satellite-derived dashboard of algae event indicators in order to create an early detection system for further algae events. And two, we wanted to provide a historical analysis of environmental proxies relevant to algae events. The ultimate goal was to provide valuable context to our partners, the City of Austin Department of Watershed Protection and the Lower Colorado River Authority. This will help them to focus monitoring efforts, guide in situ sampling campaigns, and prepare mitigation strategies. Next. In order to achieve these goals, we utilized both NASA Landsat 8 and ESA Sentinel-2 satellite imagery to create two products for end users: a water quality monitoring tool called the Lake Algae Monitoring Dashboard, or LAMDA, and a set of analyses on historical imagery, the Historical Analysis Toolbox. For LAMDA, we utilized Google Earth Engine imagery, where it was then processed, and we were able to compute our environmental proxies, of which we had 4: chlorophyll A, cyanobacteria, turbidity, and water surface temperature. To ensure confidence in these products, we validated them using in situ field measurements. The final products were then organized into an interactive mapping tool, allowing for near real-time monitoring, as well as investigation of trends. To provide historical analyses, all images up to the present were then used to probe seasonal averages and produce time series charts for partners. Next slide, please. So what does this actually look like? On the top right, we can see a set of outputs by LAMDA, our tool, and here we can see chlorophyll A concentrations of 6 Highland Lakes during the growth season, which is late spring to early autumn from 2013 to 2021. Chlorophyll production appears to peak in late summer, which makes sense to us. We can also see the upstream lakes, Buchanan, Inks, and LBJ, have relatively higher chlorophyll concentrations when compared to Travis and Austin, which are downstream. Lastly, we can see differing conditions within the chain itself. Lake Marble Falls shows continually increasing chlorophyll A concentrations, while Lake Austin and Travis are relatively stable. Different lakes have different trends, suggesting different strategies may be needed on a reservoir by reservoir basis. This is important information for our partners. Down on the bottom left is a product of the Historical Analysis Toolbox. This plot shows the changes in seasonal temperature patterns in Lady Bird Lake versus Lake Travis over the last 8 years. On average, we can observe that Lady Bird Lake is warmer when compared to the deeper Lake Travis upstream. These two outputs are just a few examples of the ways that our products can be used. There are lots of ways our partners can manipulate inputs as well as outputs to make decisions for proper mitigation strategies. Next slide, please. Technically speaking, implementing our products in Python and Earth Engine worked very well and saved an incredible amount of computing power as well as time. Our validation efforts reasonably proved our product's validity, even those with imperfect correlations. Lambda and the Historical Analysis Toolbox provide usable metrics, both temporal and spatial, to help detect near-future algal events and better understand the Highland Lake system as a whole. Understanding these seasonal, geographic, and historical trends, as well as chain-wide and individual lake dynamics, are important for creating monitoring and mitigation strategies. This problem is one that affects the environment, public health, and the economy. As such, it's important that research is ongoing to ensure the safety of the community, as well as that of our canine companions. Next slide, please. Lastly, we'd like to thank our advisors for their support in this project, each of whom were instrumental to its completion and success. Thanks so much for listening, everyone. And if you have any questions, feel free to drop them in the chat.
Wonderful. Thank you so much. I apologize. My camera kind of went out and closed off on me, but we're back. But I live very near the Highland Lakes, so I know how important this project is and how concerning it is for the community members. So it's definitely a great contribution. So next, we're going to hear about the Maya Forest Water Resources team. We're going to hear from Tamara Rudick and Madeline Savon. And you guys can get started whenever you'd like.
Hi, thank you. So hi everyone, my name is Madeline Savon. I'm on the Maya Forest Water Resources team from the JPL node. My teammates are Catherine Tafoya, Stephanie Jimenez, Laura O'Brien, and Tamara Rudick. Today, Tamara and I will be presenting our project titled Using NASA Earth Observations to Map Forested Inundation in the Maya Forest. Next slide.
So in this study, we examined inundation under the Maya forest canopy during 2008 when Central America was hit with Tropical Depression 16, which brought a lot of extreme flooding to the region. For our partners in these countries, it's important to be able to monitor wetland and flooding dynamics so that they can identify areas that are prone to variable inundation and have high flood risk, especially during extreme weather events, and so that they can plan forest management strategies accordingly to protect wetland areas. But the problem is that monitoring inundation on the ground, not even to mention in a very dense tropical forest, is really hard and really expensive. So our team then focused on investigating the best combination of methods and data for detecting forested inundation using satellite observations instead. Next slide.
Okay, so when using satellite data to look at flooded areas from space, optical imagery has its limitations. Optical sensors can't penetrate cloud cover and canopy cover, which is definitely a limitation. But synthetic aperture radar, or SAR for short, sensors operate at microwave wavelengths that could penetrate clouds and give us reliable information on the ground in tropical areas, such as the Maya forest. L-band SAR is a specific range that could penetrate further through the, like past the cloud cover and through the canopy cover to detect inundation on the ground, even in densely forested areas. Our project work focused on studying the feasibility of using SAR L-band data to map inundation under the canopy. We designed a two-step methodology to approach this task. In the first step, we used multispectral imagery from Landsat 7 and a canopy height model to classify land cover type using a random forest classifier. In this step, we produced an object-based land cover map that classified regions into 6 different land cover types. In the second step, we combined SAR L-band imagery from the ALICE PALSAR 1 satellite with the land cover classification map that we created to create initial inundation maps of the forested regions. To refine our inundation maps, we were interested in choosing a specific SAR backscatter threshold that would most accurately capture forested inundation for our particular region. So to do this, we analyzed inundation maps at 8 different backscatter values by comparing them to various field data provided by our partners, and we also compared it to a simple flood model that we created in ArcGIS. Through this process, we selected a final threshold and created our final inundation maps. Next slide.
So after our extensive threshold analysis and comparing our inundation maps to various field maps, including potential wetland layers, soil maps, and elevation data, we determined that an object-based methodology using a threshold of -5.4 for the mean backscatter value of inundated objects was optimal for detecting inundation. We generally saw really high inundation extent in June and October and low inundation in September across our study region, which corresponds really well to the average monthly precipitation values during this year. Since we didn't have access to a really robust set of validation data for inundation, we can't really say for sure how accurate these maps are, but given the limitations that our team faced, the seasonal inundation maps we generated using this methodology and this threshold showed really good agreement with our field maps and with the climate data. And the idea is that our partners can take these methods and these maps we've created to further study areas of potential variable inundation and potential wetlands. Next slide.
Okay, so in conclusion, we were able to map inundation under the forest canopy using L-band SAR, LiDAR, and optical imagery. We looked at a major flood year of 2008 to provide a proof of concept for our methodology. And as more L-band SAR data becomes available in the near future, our methods could be applied across geographic regions and time periods. And these maps of inundation could be used in various applications such as forest management and disaster planning. Next slide.
So big thank you to all of our partners and advisors and everyone who helped us with this project, and thanks for listening.
Great, thank you all so much. I've done some work on the My Biosphere using VIIRS, and I know how important it is, and the Indigenous community is really making great efforts to preserve something very special. So great job. So next we're going to hear about the Louisiana Water Resources team from Daniel Babin.
Hi everyone, so my name is Daniel Babin. I'm with the Louisiana Water Resources team, and I'm going to talk to you about a project that we did this developed term, studying and trying to preserve this barrier island system called the Chandelier Islands in southeast Louisiana. But before I proceed, I have to thank my team who nominated me to do this. It's an honor. But without Kelly Young, Taryn, Tassos, and Miriam, our project lead, this would have gone nowhere. Next slide, please. Yeah, so the Chandelier Islands, or the Breton National Wildlife Refuge, are a chain of barrier islands in southeast Louisiana. Barrier islands are important because they protect coastal regions from flooding during storms. But this one is also particularly important because the Breton National Wildlife Refuge is a national wildlife refuge. In fact, it's the second in the country. And so migratory birds use this for nesting grounds annually, and seagrass meadows there provide nursery for fisheries, which are super important to the local economy. But these islands are threatened by major storms, they're threatened by anthropogenic climate change and associated sea level rise, and they're threatened by disasters such as the BP oil spill in 2010. We're particularly interested in seagrass because it has a sort of symbiotic relationship with the island chain itself, right? So the roots of the seagrass hold the sediments that make the island together, helping prevent erosion. And there's positive feedbacks associated with its presence. So if the islands start to degrade, you'll expose the seagrass meadows, which exist behind the islands, to the elements, and they'll degrade further, causing the islands to degrade further, and so on. Next slide. So to help our partners, the CPRA, Coastal Protection and Restoration Authority in Louisiana, we made a Google Earth Engine tool, which we cutely named the Tool Creole. Tool Creole stands for the Tool for Coastal Remote Ecological Observations in Louisiana. It's built on top of another very popular tool, a successful one from JPL called the Orca tool. We added a few special features, but basically it has some of the same functionality. It's a way of easily accessing Landsat data, right? Here you see some true color images of the islands, but we added a slide comparator so you can show different parameters like turbidity or this SAV index. It's a normalized difference aquatic vegetation index dynamically from the same year or compare indices. You can also click on a point on the map and it'll render a time series given a user input date range. And so we'll go to the next slide. Get ready to see a big figure. There's a lot to take in, but bear with me. These are results generated using the tool Creel. On the left, you'll see our start date. So that's the beginning of Landsat 5 mission, 1984. And on the far right, you'll see present day, spring 2021. And already, immediately, you can appreciate the massive and profound change in land area across our study interval. But to kind of get more granular with it, we took the point inspector and got 36-year time series from each of these points on the left to get the NDAVI across time. We also use a land water classification system. So it's just classifying each pixel as land or water, and you can convert that to land area. So we also plot that over time. And whenever you compare this middle panel and the time variation in these parameters, you can see exactly which events were contributing to this kind of end product or the present day situation there. And you can see that most of this change happened in between the late 1990s and the early 2000s. Hurricane Georges, Ivan, and Katrina were particularly destructive to our area. We lost approximately 14 kilometers of land squared. That's about 80%. There's something interesting happening after the BP oil spill. There were minor restoration efforts happening. They built a sand berm. And I think this is really interesting because it highlights the positive effects, positive feedbacks that exist in the natural system, this coastal geomorphic system. After this period, land actually increased continuously. And I think this highlights the importance and potential long-term benefits of restoration projects like that. Next slide. So yeah, we hope that this tool is ultimately useful to our partners. It's important because understanding the past is key to planning and predicting the future. The tool is super useful in that the imagery is perfectly up to date, 16 days old, the Passover time of Landsat in general. And we hope that the partners will not only use it to help their planning, but to monitor restoration efforts as they're ongoing so they can assess their impacts to the environment and the efficacy of their project moving forward. And that's all. Thank you.
Wonderful. I love seeing Orca being used in new ways, and I also got to get a sneak peek of the Louisiana Water Resources story map. It's beautiful, so whenever y'all can see it, whenever it's publicly available, I highly recommend checking it out. So next we're going to hear from Isla White and Philip Casey, and they're going to be chatting about Google Colab, and they're going to be presenting their slides, so let me know if y'all need help, but whenever you guys are ready, go ahead and get started. And then we'll have a Q&A session after that.
Hello, everyone. I'm Isla White, and I am presenting with Philip Casey, and we are presenting on Open Data Cube used in Google Colab. We are both interns with the NASA Capacity Building Program.
So all of our data came from the Open Data Cube, and for those of you who are not familiar, it's an open source solution for accessing, managing, and analyzing large quantities of Earth observational data. And so it can pull from Landsat, Sentinel, and MODIS, to just name a few. And it was a program that was motivated by a need to better manage this type of data. And it has institutional support from NASA CEOS, USGS, and Geoscience Australia. So it's an extremely useful tool for capacity building because it's easy to use. Open source data means that anybody can access the observational data. And so it meshes really well with the Python API. We specifically use Google Colab And so the team had actually built a couple different products that worked with Google Colab, and we kind of built on their work. So next slide.
So data cubes are arranged in a multi-dimensional array. So along one axis, you have latitude, one you have longitude, and the other you have time. Each of these horizontal slices represents a single date of an observation. And if you travel vertically through the cube, you will be given the same location in the spatial space over time. So we have been focusing on using radar imagery from Sentinel-1 data, which has only become available in 2017. So it's not widely used, but despite this, it has some benefits over optical data, mainly being that it's not obstructed by clouds, so it has more usable data acquisition dates.
And the Maya Forest team touched on this a little bit, but so the Sentinel-1 for radar or for water detection, so you can see that it's an active sensor, so it sends out a pulse, unlike the Landsat, which is passive and detects the reflected light. And so when that radar pulse is backscattered, that's when it picks up the image, and then when it bounces off something like a smooth water, as you can see in the second image, it bounces off back into space. And so you get these really neat photos of, really neat pictures of the black of where that radar data is coming off. So yeah, this is operating at the C-band for SAR. And our project info looked at vertical horizontal polarization. Yeah, and so that was kind of the basis of our detection. Next slide.
So for our project specifically, we are focused on creating notebooks hosted on Google Colab that will allow users to quickly process data from Open Data Cube at no cost or with no coding experience. We aim to improve water extent classification techniques, especially with radar data. And since the use of radar data is less common than optical data, we have made a notebook to compare the effectiveness of Sentinel-1 data to the tried and true methods of Landsat. This notebook will be the foundations for work that will contribute to the monitoring of Sustainable Development Goal Indicator 661, which is the change in the extent of water-related ecosystems over time. And so we're going to have a little demo for everyone of our notebook from this intern session. If you want to take it away, Philip.
Yeah, so this is a little quick fix. We had some issues going into it, but as you scroll down, so this is all during the Google Colab platform. So it's like if you go onto opendatacube.com, you can access the Google Colab scripts, and it just any kind of person with a Google account can go and run and modify those. So this beginning here is just loading the data. As you go down, this is the part that you could modify. We have a couple different case studies. This case study we're about to show is from the Amazon state in Brazil. It's a river that has seasonal flooding during the rainy season. And so this is just kind of an image to see what you're looking at. So you can see this is from the Google Earth engine. So if you continue to scroll down, so this is where both the Landsat and Sentinel data is loaded. So we have just a quick comparison of looking for dates that they align up. So with those kind of coincidence dates, we can use the analysis to validate whether or not that we're actually getting all the Sentinel-1 radar detection compared to the Landsat water detection. As we continue to go down, we use ASU to do an automatic thresholding. So it's an image kind of processing method that minimizes the variance between two classes. And so in this case, it's between water and land. And so that is actually worked pretty well for this image, but we also have an option that you can manually threshold just depending on the land around the body of water. It can kind of alter about what the sensor catches. And so you can see a histogram of the backscatter intensity right there with indication of where our threshold is. So so that the radar is generally pretty noisy. So we used a block filter, which helps kind of despeckle the process. And you can actually switch it for a couple different sizes. So it can, depending on your land cover need, it can alter kind of what you're catching there.
And so just to demonstrate sort of the interactiveness that this notebook will have once it's published in the sandbox space, we'll have the base of the data loaded, but you can add in whatever you want and you can change it and customize it. So we have loaded this graph specifically for our water threshold, but you can change it. So if this is the recommended threshold level at 20, this one is a little bit different, but you can run it at different thresholds by changing this number here and then rerunning the code, and it will output a different image. So you can select the best one for your data set. And all of that we have clearly labeled throughout the notebook. And then we have compared it to modified normalized water index, where we have a similar histogram to determine the threshold limit. And that is also something that you can change very easily and output a Boolean map of the same. And then as a validation, the water observations from space, or WOFS data sets for water classification, is sort of the gold standard for water classification, and it uses, we have used it with Landsat 8 data. So this is where we're between this here and up here, we are calculating Booleans with the Landsat data and classifying them, where we will later display them against each other and do a validation. So down here, we can see what we have run and how the OTSU, the VH thresholding, the MNWDI, and the WOFs have all compared with each other, and how well they have done in comparison to determine if the radar data is being as accurate or very similar to the Landsat data. And right here is a pixel count of those values. So you can see how much water is actually classified, and you can compare those to the WOFs.
So this is just a quick comparison of a couple of different of the block filters. And so as you see, as you increase the block filter number, you get less backscatter, but you do lose a little bit on the edges as you continue to increase. So for this case, the optimal would probably be around 7, but it would probably be different for for different cases. And then our last little thing, or actually, so this is just a little validation. So this is comparing the WOFs to the Sentinel-1 with a 5 and 7 block filter. And so you can see the green are kind of the mist, and the reds are the false alarms, and the blue are where it crosses over. So there's a little bit on the edges, a little bit of issue, but overall it's pretty close.
And it is important to note that in this notebook, in order to compare the two, we had to change the resolutions of Sentinel data. So Sentinel data actually has a higher resolution than Landsat 8 data, and we sort of had to handicap it in that way and load it at a smaller resolution so it would be at a comparable extent to the Landsat data. So hopefully running in a true environment where Sentinel is running as strong as it can, it will be at a even better extent than this and able to detect better. And so from this, our applications that we're hoping to do is look at water extent over time. So we've created this section where we calculate the Boolean of water class extent over your time series throughout the data cube. And we have come up with a summary of, for each time slice, what is the quantity of water pixels in that scene. So as you can see, in this case in Brazil, we have a peak at the beginning of the data and slowly start to lose water quantity over time. And that is our notebook that we've been working on this semester. And we wanted to have a shout out to Brian Kilo for helping us through all of this and teaching us how to use Python, because none of us had any experience. But all of this project should be shareable and usable, and you are able to view similar data to this or similar notebooks to this on the Open Earth Alliance page.
Wonderful. This is incredibly impressive. I am so excited for the developed participants to be able to use this. I can see it being very applicable to a lot of our projects. So you should be really proud of the work y'all did, especially with no prior Python knowledge. That is very impressive. So now we're going to move into about a 10-minute Q&A session. So if you've got any questions for the water resources teams that we just heard from, or the capacity building interns for the Google Colab content, feel free to type it into the chat, or you can raise your hand or just get to asking.
So Jonathan asked in the chat if we could split the Landsat pixels to go higher resolution to match the Sentinel. And this is something that we were just thinking about today. Didn't necessarily want to tweak the code too much to do something that might crash the whole notebook, especially because there's been a lot of changes with DataCube recently. So yes, we are hoping that maybe there is a calculation that can be done that will expand the resolution of Landsat, so it's handicapping Landsat instead of Sentinel, because that's really what we want to be focusing on.
Great. I've got a question for the Coastal California Water Resources team. I'm curious about, I know very little about estuaries. I'll start there. So how reproducible is this project to other estuaries? Are they so unique and kind of fragile that it's difficult to reproduce and would require additional work? Or could you just take this and use this like in Texas for their estuaries?
Yeah, so I can talk a little bit about this, but if my team members want to jump in, feel free. So our tool is specifically designed to be reproducible for other bar-built estuaries. So as long as it's bar-built, our project is designed to work for that. And so we do have an option in our graphical user interface to upload shapefiles, and we have a tutorial on how to create those. We should note, though, that from our analysis, we've seen that larger estuaries tend to work a little bit better. And we tend to see better results with those. So that's kind of our recommendation there. But yes, we definitely have some, we hope that it will be reproducible for our partners and that they can do it for other sites.
And I apologize, could you expand on what bar-built means? Maybe there's somebody else in the crowd who also is unfamiliar.
Yes, of course. Good prompt. So bar-built estuary implying that it's intermittently open and closed. So there are times of the year when the river won't be flowing into the sea because of reduced precipitation and other seasonal trends. And then the sandbar blocking it off. But someone could probably give a much more eloquent explanation. But yeah, that's kind of some of the rough explanation of that.
If I could jump in with another question for the Coastal California team. Funny enough, I actually live about 15 minutes away from your estuary of study. And so with the recent wildfires that we've had, a report I did and my senior thesis was looking at how wildfire was affecting the river. And I was wondering if you all had noticed any drastic changes with perhaps inundation or sediment load following the most recent Walbridge fire in 2020, August 2020.
I can chime in. That's funny that that was your thesis because mine was wildfire and coastal water quality in Southern California. So we didn't incorporate fire data, but we did notice that there were some instances when there were turbidity peaks that were much more variable compared to the rest of the data set, compared to when we were looking at the discharge data. So you'd see huge turbidity peaks, and then you look at the discharge, and it was actually a kind of a small peak. And so I think that would be something that could be influenced by fire. But definitely that would be a really cool further analysis.
Absolutely. Thank you.
Daniel, if you want to go ahead and ask your question.
Thanks, Alexa. I have a question for the Google Colab folks. I was wondering if you guys could just talk more in general about data cubes and what's going on with that project and your kind of involvement with it / application of it. I'm not super clear on that, but it sounds really interesting. I also like that it's running in Python. I'm like a big Python nerd, and I have some ideas. But yeah, I just want to know more about it.
Oh, sorry, sure.
You can go ahead.
Yeah, so we probably are not the most knowledgeable ones to ask about the whole thing, but we can give a brief overview. So yeah, it was a project kind of born. It seemed like out of necessity to manage the the large amounts of satellite data that were there, and so I think that it was out of it was a Landsat product to kind of manage all of that. And so yeah, it's just it's open. It's if you just go, we can put the link into the. Brian just did put the link in the chat.
Yeah.
And you can learn all about it, and it takes you. There's a GitHub repository, and you can go over and look at the Colab notebooks. And yeah, it's all there. I'm sure if you have any more to add there, Isla.
Yeah, so data cubes, basically this website, what it is a collection of data cubes. And data cubes are pre-processed data, analysis-ready data, so you should be able to directly analyze that pretty quickly. And it's a combination, like I was saying, through space and time of a data set. So it's all like pre-packaged in this nice little box. That's like the perfect metaphor for it. And it's very usable, and having it be open source on this site makes it very accessible to all populations.
That's really cool. Yeah, I was wondering because I use Xarray a lot. I'm not sure if you guys have heard of this Python package, and it basically does cubes too, but it's really difficult to do. And there may be Xarray running under the hood and some of this stuff, but it's really difficult to do GIS stuff like roster data in Xarray. So it sounds really exciting.
Yeah. Oh, sorry.
Go ahead.
Yeah, it's definitely a workaround and not necessarily super intuitive, especially if you are formally trained in ARC products. But it's definitely, once you get going with, we use, if you work off of these notebooks, it quickly shows you how to use this data. And so you can actually use the bases of these notebooks and work them into your own in the Google Colab environment for free. And it will all run the same, and you'll be able to completely customize it and save it. So it's a pretty amazing tool.
Thanks so much.
Awesome. This is, I'm so excited to hear about this product. Jonathan, I see you have a hand up.
Yeah, sorry, this is Another question for the Google Colab team. So those pre-processed data cubes, I know Colab is a Google Earth Engine thing. So are those pre-processed data cubes available in Google Earth Engine catalog, or is there another way that you're accessing those? They are? Okay, cool.
So in the
Thank you.
Yeah, in the Colab environment, we're working through Google Earth Engine. You can access Open Data Cube through your Python code in other ways outside of Google Earth Engine, but through Colab, you just can link it straight into there and not have to, worry about it.
Okay, awesome. Thank you.
Okay, if nobody else has questions, we're going to continue, and we're going to go with some more of the capacity building program. They're going to cover story maps. We've got Arlen Arpero, Teresa Perlero, I'm so sorry if I pronounced that incorrectly, and Shilpa Cannon.
I'm gonna share my screen, that way we can do our presentation and then also demo the story map that we created. My name is Teresa Perello, and I am an environmental science major at NC State.
I'm Arlen Arpero, and I'm a geography major at the University of New Mexico.
And I'm Shilpa Cannon, and I'm a Management of Information Systems major at San Jose State University.
And as stated earlier, we are interns with the capacity building program this summer. And one of our projects as a team was to create a ArcGIS story map for the capacity building program.
So what is a story map? A story map is an ArcGIS online product made by Esri, a GIS company, and you use maps and other multimedia like pictures, videos, and text to tell a story. To create a story map, it is really easy with a simple and user-friendly interface, so anyone with no prior GIS experience can hop right in and learn really easily. So it is better for people who are visual learners, and it has many uses like call to actions for organizations, tutorials for schools, portfolios for personal use as well as business use. But the capacity building program is using it to get the public to learn more about the program, the history, the projects, and the people. So we were assigned to make this story map, and I'll pass it to Teresa and Shilpa to explain the process of how we did it further.
So we started by dividing up our 8 intern team into the different program areas we wanted to highlight for the capacity building program. And this meant that each person on our team got experience doing research to collect the content, as well as conducting interviews about the people that we were going to be highlighting on the page. For collecting information about each program's history, we used the existing program websites, annual reports and summaries, as well as some press releases. For the projects, we also used existing program websites and annual summaries, while also looking at project archives and then asking our interviewees about the projects that they personally have worked on. Lastly, to highlight the people, we used their profiles that happened to be online, as well as conducted interviews, and Shilpa will go into more detail about our interview process.
Going into our interview process, we've divided it up as our pre-interview setup, actual interview process, and post-interview video editing and content collection. So first, with the pre-interview setup, we conducted initial research on the interviewee, developed a questions document, and tested video recording capabilities through Teams. Next, with the actual interview process, we provided our self-introductions to the interviewee, requested a program overview and position description from them, presented our actual interview questions, checked for story map content that they may want us to include, and also asked for any final questions. Finally, during the post-interview video editing and content collection portion, we shortened and edited the resulting footage, included personalized additions to the video, such as a title screen, background music, and captions, and finally included content within the story map as needed. So now I'll hand it over to Teresa to start off our capacity building program story map demo.
So the story map opens on this page, which explains what the capacity building program is at NASA. So it is a focus area of NASA's Applied Sciences program and a part of the Earth Science Division at NASA. And then here are the tabs for each program. And we started with the capacity building program tab because it is a general overview of the program as a whole. The capacity building program was formed in 2011 and adopted RSET Develop and Severe, while the Indigenous Peoples Pilot was later created in 2017. Their goal is to make Earth observations more accessible and help individuals and institutions have the capability to use Earth observations data. CBP also works with many organizations around the world to help with this. And we linked their website here, that way people can learn more about them in detail. This is a collage of images that we included from different events and the programs that the capacity building has. We then summarized each program very briefly. We chose to keep it short on this tab since we will go into more detail on the later tabs. And then we included a map of the various countries the capacity building has worked in, and many of the countries have had more than one project being done. We also included this quote from Dr. Karen St. Germain, who is the director of the Earth Science Division. She said this during her opening remarks in Applied Sciences Week last year, and we felt that it greatly summarized the importance of the work that the capacity building does. Lastly, we highlighted the people of the capacity building, which are Dr. Nancy Searby, the program manager, and Sydney Neugebauer, the coordination and analysis lead. We also included parts of our interview with Sydney because she has worked with the capacity building and developed for many years. And then we also linked Earth Science Applications Week and credited the creators of this tab specifically, who are Hannah Wetzel and myself. Now, Arlen will go over the RSET information.
RSET stands for Applied Remote Sensing Training Program, and this tab was created by our fellow interns Isla White and Philip Casey, where they highlighted a brief history of RSET, where they started in 2009 and have since then reached over 65,000 participants from 176 countries. On the left, you can see a little video explaining more about RSET, and once you click the link in the comments, you can explore all the videos since we don't have time to watch them with everyone. They also included a link to the RSET page, as well as their application areas down below. On the right, you can see how they have had over 130 trainings in the past 10 years, and every year they host more and more trainings. So their application areas include health and air quality, water resources, disasters, and land. They also chose to interview Brock Blevins, the training coordinator of RSET, and he explains the future of RSET. They also highlighted success stories, which include Sarah Strachan, who created the Idaho Wildfire Smoke Portal, and you can actually interact with that tool in the background of the story map, as well as Christina Karen Ovando Crespo, who uses RSET trainings to help local governments, indigenous communities, and the trainings for lectures. Finally, they have Facundo Casasola, who is from Argentina, and he took the training himself and gives his testimonial on it. I'll pass it to Teresa to talk about the Develop tab.
So the Develop tab was created by Ella Hogan and Monica Namo, And they started off with the history of the Develop program, since it was created after 3 interns wrote a research paper titled The Practical Applications of Remote Sensing in 1998, and Develop was officially created in 1999. They are headquartered at Langley Research Center, and they've helped thousands of people over the past years of their existence. They celebrated their 20th anniversary in 2018 by planting a tree with a plaque that read, "In recognition of the 20th anniversary of the Develop program, a sturdy tree grows with a little help from my friends." They also included the interactive map that Develop has, which allows you to see the nodes that Develop has across the country. Since the interactive mapper is quite large, they included a link to Develop's interactive mapper so that people can explore it more. We highlighted Mike Ruiz, who is the program manager of Develop, as well as Laura Childs Gleason, who is the science manager. And then we included an interview with Mike and Lauren. The projects that Develop has done is through their 10-week internship program. And so this is a brief overview of the internship program, and then it explains some of the projects that have been able to be completed through that program, such as the work that is being done in Bhutan, as well as their partnership with Groundwork USA. Lastly, Ella and Monica highlighted the career progression that Develop has given some of its participants, such as recently Chloe Schneider and Ebony Williams, who worked on projects this spring, Beth Brumbar, Lauren Childs Gleason, and Amanda Cutright, who actually was an intern in 1999, the first year that Develop was active. And then here's the link to Develop's website so that people can once again learn more if they want to. And now Shilpa will go over the Severe tab.
The Severe tab was developed by me and Arlen Arpero, and right below the opening image starts off with a short 2.5-minute long video about what Severe actually is, and also includes a link to the official Severe website underneath it. Next, we included the history behind Severe's formation, and if you scroll further down, there's also a map that goes along with the history that depicts all of the locations of Severe's projects. This includes background information behind the location's development, as well as the year that the location was established. These total up to 6 different locations around the world as depicted on the map, and 5 of which that are currently active. After that, we have Severe's project section, and this primarily highlights the different categories of projects Severe undertakes, as well as any links to their other endeavors, including their global data catalog, ISERV, and their trainings page. All of the links to that are right here. Finally, the last section highlights all of the people involved in Severe, which includes Dan Irvin, Tony Kim, Ashutosh Limaye, and also features media related to these individuals, which includes our interview with Tony Kim on his experiences at Severe. And once we go through that, I'll hand it over to Arlen to go over our final Indigenous Peoples Pilot tab on the story map.
The Indigenous Peoples Pilot is the newest addition to the capacity building program. They joined in 2017, and their mission is to communicate with Indigenous communities so that way the IPP can provide NASA resources to cater to their needs. We conducted an interview with Cindy Schmidt, the IPP lead, and she shares her experiences working with IPP as well as her goals for the future. We also created an interactive mapper where you can click on each of the diamonds and explore the projects, trainings, workshops, and other activities across the United States. And the light blue identifies the tribal lands in the United States they have worked with. We also included a global map to show that they have reached outside of the United States with countries worldwide. We also chose to include projects including online trainings, in-person trainings, and involvement with organizations where they present and create sessions in these conferences. We also chose to highlight the DSET tool, which is a creation of the Western Water Applications Office. And we included a picture of how it looks, as well as an explanation by Nikki Tully, who is a research assistant. And we also interviewed Nikki Tully, and you can find that there. Finally, we decided to include the people. Their team is small but mighty, and it makes up of Cindy Schmidt, the project lead, Amber McCullum, the team member and engagement coordinator of IPP, and finally, James Rattling Leaf Sr., who is a member of the Rosebud Sioux Tribe and founding member of the Geo-Indigenous Alliance. That concludes the story map, and I'll pass it to Shilpa to wrap it up for us.
We hope you enjoy the effort that all of our interns here at the Capacity Building Program put into the story map, and that it continues to not only educate those interested in the immense work that RSET, Develop, Severe, and the Indigenous Peoples Pilot put in their projects, but also conveys information that effectively relays the successes behind all of these programs. As a final reminder, the link to the story map should be right in the chat. Thank you, and now we will be opening up the floor to any questions from the audience, either from verbally unmuting or through the chat if there's a if there's a sufficient amount of time for us, but if not, it's totally fine if you're running short and we can move forward to the next project.
Wow, great job. I love seeing everything being done in the capacity building areas of NASA. I think it's really incredible and very important, especially with Indigenous communities, to work and elevate them. Does anybody have any questions? For now, I think we are going to continue moving. And if you still have questions, feel free to save them after these last bit of flash talks. So we're going to be moving from water resources to transportation and agriculture. First, we're going to hear from the Florida Transportation and Infrastructure team, and we're going to be hearing from Michael Enns.
Thank you so much, Alexa. Hello, everybody. Just to reiterate, my name is Michael Enns, and I'm a part of NASA's Develop Florida Transportation and Infrastructure team, working out of the Ames Research Center in California. The other members of my team include Ben Rocha, our project lead, Melanie Leung, our data manager, Estenia Ortiz, and Alexis Smith. Today I'll be presenting our results in building a Google Earth Engine tool to assist in the advancement of monitoring water quality along southern Florida seaports to assess impacts on coral reef tracts from harbor deepening projects. Next slide, please. The Florida Reef Tract, shown above, is the only living nearshore barrier coral reef system in the continental United States, making it a high priority for protection and conservation. The Reef Tract provides pivotal protection to the Florida coastline, along with recreational and commercial services. Having declined by more than 80% since the 1970s, any potential impacts on the reef require careful monitoring and mitigation when possible. Located in Fort Lauderdale, Florida, the planned 2022 Port Everglades dredging project, to be conducted by the U.S. Army Corps of Engineers, is anticipated to directly impact about 30 acres of the Florida Reef Tract directly outside the port's mouth, and potentially indirectly impact up to 564 acres of the surrounding seabed. Excuse me. Our research partners for this project, the U.S. Army Corps of Engineers and the National Oceanic and Atmospheric Administration's National Marine Fisheries Service, are interested in establishing historical baseline parameters to address concerns regarding the potential impacts of dredging on the reef's health, while also balancing the area's economic prosperity. Next slide, please. To establish historical baseline averages across multiple water parameters, our data acquisition process began with determining which satellites we could use to cover the large temporal and spatial scope of our project, which was about 20 years. We chose to use 5 different satellites and sensors to ensure the highest quality of temporal and spatial resolution. Landsat 5, 7, 8, Sentinel-2, and Aquaterra Modus were chosen for imagery. The timeline at the bottom of the slide illustrates the period for which each satellite provided data, color-coded. In general, these parameters were determined by Landsat 5, 7, and 8 for the years 2000 to 2020, and by Sentinel-2 for 2015 to 2020 as well. Next slide, please. Our team incorporated NASA Earth observations into a graphical user interface in Google Earth Engine that can generate time series analysis and imagery for water quality parameters based on JPL 2019's Orca tool. We named this interface the SHARC tool, also known as the Seaport and Harbor Area Resource Quality tool. The chart tool allows users to look at and analyze imagery and time series charts of different water quality parameters over a specified time and defined study area. The parameters chosen for this instance of the tool include turbidity, diffuse light attenuation coefficient, or KD490 as it's generally known, chlorophyll A, exclusively on sentinel imagery, colored dissolved organic material or CDOM, sea surface temperature provided by MODIS, and normalized difference indices for turbidity and chlorophyll A. Next slide, please. After running the Shark tool, we generated the following time series analysis charts for all parameters, but only showcase turbidity and chlorophyll A levels here from January 2000 to January 2020. From these charts, we were able to identify historical baseline averages, seasonal patterns and trends, as well as anomalies and events. These charts also provided us with correlating data sheets for each parameter utilized for further analysis and validation. From there, our team plugged the data values generated for turbidity from our time series charts into Microsoft Excel for cross-validation with the limited in situ data that was provided to us by our research partners. For thoroughness, we corrected and ran our two data sets through a percent difference analysis, root mean square error analysis, as well as a linear regression analysis. From those tests, the two sites returned a 0.58 and 0.32 root mean square error respectively, and held an average of between 1% to 12% difference between satellite and in situ measurements, showing a strong beginning but expressing a need for improvement. Next slide, please. So based on the work conducted, we were able to establish historical baseline levels for most water quality parameters across the entire 20-year time range, useful to our partners for establishing thresholds of what could be considered dangerous conditions during periods of dredging in the future. Ultimately, our team concluded that satellite imagery analysis can be a useful tool to produce historical benchmarks for coastal water quality parameters with relatively accurate results and low recurring costs. Beyond this, we learned validation of remotely sensed water parameters is highly contingent on large quantities of corrected in situ data. Finally, we found that the satellite imagery paired with Google Earth Engine has the potential to increase the ability to conduct research while simultaneously decreasing cost and time requirements for projects like these. We would like to thank our science advisor and fellows at Ames, Dr. Juan Torres Perez, Haley Pippin, Brittany Beaudry, and Erica Kreiner, as well as our project partners at the National Oceanic and Atmospheric Administration and U.S. Army Corps of Engineers for their guidance throughout this project. We hope the Shark tool can be used to support greater coral reef protection and improve decision-making regarding dredging in the future. Thank you so much.
Okay.
Great, thank you, Michael. That was very interesting. I feel like the Orca tool really garners some great names from the people that are adapting it. It's very impressive. So next, we're gonna hear from Justine Spohr on the Tonle Sap Food Security and Agriculture 2 project.
Awesome, thank you so much. As Alexa said, my name is Justine Spohr, and on behalf of Nick Palacio, Brian Place, Molly Farrell, and Joey Lindsay, I will be presenting on the Tonle Sap Food Security and Agriculture 2 Develop project. Next slide, please. So here's where our project is located in the world, the Tonle Sap Basin in central Cambodia. Tonle Sap Lake, which is shown in our study area map on the slide there, is the largest lake in Southeastern Asia and provides critical ecosystem services to the whole region, including fisheries, agricultural irrigation, and biodiverse habitats. Deforestation, increased pumping for farming, and the development of hydroelectric dams in the region threaten the health of the lake and therefore food security in the entire region. Our two partners for this project are Conservation International and the Tonle Sap Authority, and the objective of this three-term Develop project is to implement Conservation International's Freshwater Health Index, or FHI, to the basin using remotely sensed data. The Freshwater Health Index scores watersheds across a variety of sectors to prioritize resource expenditure and conservation efforts. And our chunk of the project will focus on analyzing ecosystem vitality sub-indicators within the Tonle Sap Basin. Next slide, please. So we aimed to focus on two FHI sub-indicators with remotely sensed data: groundwater storage depletion and water quality. For water quality, we used a soil and water assessment tool, or SWOT model, to look at water quality and develop a methodology for calculating groundwater storage depletion from the GRACE satellite. The SWAT model requires 5 inputs: a DEM, land cover classification, precipitation, air temperature, and soil classification. We were able to get 4 of those 5 inputs from remotely sensed data. Only the soil classification was something that we couldn't acquire by satellite. The soil classification is the image on the top in our slide, and a land cover classification that was developed by the first term of this project is the GIF on the bottom. Each of these data sets had to be pre-processed before input into the SWAT model, so we created a Python API that combined Google Earth Engine data acquisition with output formatting from Python. This script will allow end users to leverage remotely sensed data when looking at water quality in the framework of the Freshwater Health Index, ideally in locations other than the Tonle Sap Basin too. For groundwater storage, we used GRACE satellite data, which measures total terrestrial water anomaly, and isolated groundwater from that by subtracting soil moisture, plant canopy intercept, and surface water, all from the Global Land Data Assimilation System dataset. Because GRACE provides its data in terms of anomaly, we had to process each variable into an anomaly value by creating a baseline first. Then we used a Landsat land and water mass to weight each GRACE pixel according to their proportion of land and water. And after all of those processing steps, we were able to subtract each of those surface water variables from GRACE to isolate the groundwater anomaly. Next slide, please. So the image on the left shows a groundwater and surface water storage map for Southeast Asia that was created using the GRACE data. And below that is the equation that we used to develop our methodology. Change in groundwater equals change in total water storage minus change in surface water, change in soil moisture, and change in plant canopy intercept. Monitoring groundwater over time in the basin will provide insights on water scarcity, especially during the dry season when it becomes more stressed. The image on the right is an example output of nitrate flows in the Tonle Sap Basin over a 6-month period that our SWAT model outputs. The SWAT model calculates nutrient flows based on hydrologic response units, which are indicated by the different thicknesses of streams in that image. The SWAT model provides both inflows and outflows from the basin for a variety of variables. And for our FHI analysis, we focused on nitrogen, phosphorus, and suspended sediments. Next slide, please. Due to the regional importance of Tonle Sap's freshwater resource, monitoring its health and vitality is crucial to its protection and management. The Freshwater Health Index relies heavily on in situ data. However, because of COVID-19, our partners weren't able to collect field data, and so using this remotely sensed data helps fill those gaps. This methodology could also be useful in non-pandemic times as well, because in situ data collection can be time-consuming and costly. FHI analyses in general are extremely useful in areas with limited in situ data or monitoring programs because they provide a baseline of ecosystem vitality measurements to assess change over time. Having a quick, efficient, and reliable method of measuring freshwater health in the Tonle Sap Basin is necessary to inform policymakers and protect a resource that provides for millions of people in the region. Next slide, please. And lastly, we'd just like to acknowledge all the wonderful people that helped us on our project. We are so grateful for all of your expertise and skills. Thank you so much.
Thank you. That was very informative. I think it really highlights the use of remote sensing's resiliency in the face of change. And I imagine it'll become increasingly more important as water scarcity continues to be an issue. So next we're going to hear from Ryan Lamb and Tyler Pantel for the Argentina Food Security and Agriculture Project.
Awesome. Thank you so much, Alexa. Once again, my name is Tyler Pantel, and I'm joined today by Ryan Lamb to present on behalf of Brooke Egley, Sienna Templeman, and Caroline Williams for the Argentina Agriculture and Food Security team. We're very excited to share our project today on crop monitoring and forecasting for Argentina using NASA satellite observations. Next, please. So for this project, we partnered with the Buenos Aires Grain Exchange, a nonprofit organization down in Argentina responsible for both weekly harvest reports and end-of-season crop yield estimates. With their input, we created end products and tools that addressed 4 main community concerns. First, the Grain Exchange needed an easier way to accurately forecast crop yields across the 15 agricultural zones they monitor, with a focus on the 6 core zones highlighted on the map. Because Argentina is a major producer and exporter of soybeans, corn, and wheat, accurate forecasting is crucial to national crop management, as well as regional and global food security. Second, the Grain Exchange currently has an abundance of data across these 15 zones, and they needed an easier way to process and analyze these large data sets. Third, crop yields are directly impacted by climatology and environmental factors, including the El Nino Southern Oscillation, or ENSO. So it's crucial to provide our partners with a tool to understand the climatological impacts during the growing season. And lastly, the Grain Exchange wanted to address current limitations on data processing, which can cause useful and applicable data sets to be rendered unusable. So we conducted our entire project through Google Earth Engine, a web-based data processing platform, in order to resolve the technical needs for data processing and make our outputs more widely accessible. Next, please. For this research, we leveraged the iMerge constellation for precipitation data, SMAP for an integrated data set of remotely sensed and in situ soil moisture, and Terra Modis for both land surface temperature and NDVI, or Normalized Difference Vegetation Index. We combined these NASA satellite observations with ancillary data sets from our partners that included agricultural zone shape files and crop yield data. Our team then developed a 3-part toolset on Google Earth Engine that included an autoregressive NDVI forecasting model, a linear regression crop yield forecasting model based on our predicted NDVI, and a climate variables time series and mapping tool. These tools can assist our partners at the Buenos Aires Grain Exchange with predicting crop yields and understanding seasonal variations in climate variables that are critical to crop development. Next, please.
Here we have the 3 different outputs from our script. On the left-hand side, we have the climate variable tool, which outputs plots and maps at different temperature, precipitation, soil moisture, as well as NDVI for different zones and timescales. So if you wanted to do zone 3 and a time period of 2020 to 2021 or 2012 to 2021, it's highly customizable to go ahead and look at trends. This allows the user to generate customized plots based on their needs. The map here displays the average temperature in zone 6 for the recent 2021 or 2020 to 2021 growing season. In the middle, we have our NDVI forecasting tool, which is capable of predicting NDVI 1 to 6 months in advance, although 2 and 4 month forecasts have the highest accuracy. The plot here shows the linear regression between the actual and predicted NDVI with an R-squared value of 0.89 for zone 6. On the right-hand side, we have the crop yield forecasting tool, which examines the linear relationship between NDVI and crop yield, using the forecasted NDVI to predict end-of-season crop yields. The graph here displays the relationship between average maximum NDVI in zone 3 and soybean yields. The correlation for each crop type and zone is highly variable, and the R-squared for this plot is 0.8, so highly correlated. Next slide. As far as conclusions, among the climate variables, they're able to exhibit different patterns throughout the growing season. For the NDVI forecasting, the model is capable of forecasting NDVI 2 to 4 months in advance for the growing season with high correlations. And for the crop yields, the relationship between NDVI and crop yield varies for growing zones and crop types with R-squared values exhibiting moderately strong correlations. Our scripts Our scripts contribute to a better understanding of the relationship between climate, NDVI, and crop yield. As for the end user benefit, one of the most important things for us in the develop program is that the GE tools will provide information on the region's climate, soil moisture, and vegetation conditions. Additionally, these products aid the decision-making process by monitoring vegetation health and estimating end-of-season crop yield for the Grain Exchange so they can better inform their various users and actors, including farmers, local governments, producers, market analysts, and policymakers. Next slide, please. Lastly, we want to thank our partners at the Buenos Aires Grain Exchange, our science advisors at Goddard Space Flight Center, and our fellow. Thank you very much for your time, and back to you, Alexa.
Thank you, and great job, you guys. This is really important and really strengthens our relationship with other countries, which I think is just fantastic and a key thing about Develop that I love. So now we're going to move over into one of our capacity building programs, our sister program. Helen Parash will be speaking. She'll be giving a flash talk. And whenever you're ready, you can go ahead and take that away. Oh, actually, let me take myself away from sharing the screen. Okay, you're probably good.
Oh, fantastic. Thank you so much. Let me just share. So it says that I don't have the sharing ability.
Let me see how to add you. I don't know if Amanda or Lauren are still in here. I know they.
Yeah, hold on, trying to find it. Oh, Baldwin is what she's under. Cool, you should be fine, yeah.
Awesome, thank you guys so much. So hopefully you can see my screen okay, and it should be moving into presenter mode any moment. All right. Well, thank you so much for having me. I'm Helen Parachi, formerly Baldwin, so that is a little confusing and my apologies. I'm going to be talking about my thesis work, estimating forest stand height with L-band SAR or synthetic aperture radar data in Savannakhet, Laos. I did this work under the NASA Severe program. So as mentioned, NASA Severe is within the capacity building program in NASA, a sister to Develop and RSET. It's a lovely sisterhood. And we we have 5 hubs across the Asia, Africa, and the Americas regions. And we also do other activities that are more globally focused. So the SAR handbook is one of those. The SAR handbook contains the inputs from different leading SAR experts that focuses on comprehensive methodologies for forest monitoring and biomass estimation and communicating those to different researchers who maybe the entry level for SAR is a little bit challenging because SAR is so different from the optical imagery that we often see. The objectives for this project were to estimate forest stand height using the methods presented in Chapter 4 of the SAR Handbook. These were developed by Paul Siqueira and Yang Lei, and I wanted to apply these to a severe-focused country, as previously they had only been applied to the United States in central Maine. And I wanted to assess to what extent these methods added information that was beneficial for estimating tall trees. And finally, well, not finally, I want to provide insight into data acquisition and performance challenges associated with these methodologies. And I also wanted to compare these estimates with other products, such as the Spaceborne LiDAR JEDI and the Global Land Analysis and Discovery tree cover product. So here is an image of my study area, and I've also included the extent of the different input data sets here. So I selected Lao People's Democratic Republic, Lao PDR, as it is a severe Mekong focused country, and they have experienced deforestation and degradation. Deforestation due to agribusiness, tree plantations, mining, and hydropower projects predominantly, whereas degradation is primarily driven by shifting cultivation by small-scale farmers. I specifically looked at a section within Savannakhet province. Within this province, tree cover reduced from 70% to 41% from 2000 to 2010. And you could see the extents here of my input data sets. So my data sets were collected for the year of 2009. And I have the area of the annual mosaic from ALOS Pulsar, as well as the level 1 or raw data from ALOS Pulsar. We also used LiDAR data available for the region through our partners through Severe Mekong for this Dong Sithwain production forest. And then we had a couple comparison data sets, which extended the GLAD data set extended for this entire area. And then we also compared with the JEDI data level 3 data set. So it was only available for these darker areas here. So this is a simplified version of my methodology, but basically we took that annual mosaic from ALOS Pulsar and applied the backscatter technique, which relies on the assumption that as the higher a forest, the number of scatterers and therefore the backscatter power will increase, and thus it allows us to create a relationship and estimate forest stand height. And then we applied the INSAR technique to the level 1 ALOS Pulsar data, and this relies on the assumption that when we have 2 passes over the same location of radar, that there will be more movement between those 2 passes if the trees are taller. This will also allow us to create a relationship and estimate forest stand height. Then we fused those 2 estimates together using backscatter below 10 meters and the INSAR-based forest stand height above 10 meters. Really, what Paul Sikera and Yang Lei show in their case study in Maine is that there is a lot of benefit from including INSAR, as backscatter tends to saturate at higher tree heights. And then we compared these final estimates with other data sets, which I'm just giving a very small glimpse into our results, but here I have it highlighted comparing with that initial case study conducted in Lei et al. 2019, which our backscatter, the R-squared, performed worse compared to their R-squared of 0.4, and however our INSAR compared very comparatively compared to their R-squared of 0.17. And so in terms of R-squared, our results were similar to what we would expect, not so much in the backscatter, but in terms of the benefits that INSAR potentially could give us. However, when we looked at the distribution of heights, we found that the INSAR estimated heights actually saturated before the backscatter estimated heights. And we believe that that has to do with the data quality and quantity available to us. And so we're looking forward to the NISAR mission, which may alleviate these issues, which we presume to be due to a long temporal baseline between the 2 images that we were able to use for the INSAR technique. And I want to bring this a little bit back towards user engagement, because this is something that this is a technique that we're continuing to refine and continuing to work with as we use the SAR handbook and have done many workshops globally. Tim Mayer and I hosted one in January 2020 on forest stand height at Sevier Mekong, and I have a picture of it here. And from feedback from our partners and through our continued studies on this and applying it to different locations, we're continuing to develop these techniques. So with that, thank you very much. And I would like to acknowledge the Severe Science Coordination Office, Severe Mekong, some specific people who are assisting with this project, and especially Dr. Yang Lei, who assisted me a lot with this. Thank you very much. That's it.
Thank you. I love hearing about what the sister programs are doing. I think it's great that there's so much collaboration and continuous work done. So at this point, this concludes the formal flash talks. We're going to open it up for a Q&A session. If you've got any questions, feel free to raise your hand or type into the chat. I want to thank you all for your time. This was such a great experience. I love seeing what everybody's doing. I develop. And yeah, we've got a question from Jenna.
I have a question for the Tonle Sap team. What years did you guys use as the baseline for your groundwater model? Because you said you had like a baseline and then an anomaly.
Yeah, the GRACE data collects its baseline from 2004 to 2010. So we did the same for all of the surface water variables. The study period for our whole analysis, as you know, you were on the first term, was 2000-2020, but the GRACE data is only available from 2002 to 2017. And so we had to sort of make do and do what we could with that data availability.
Awesome, thank you.
I've got a question for the capacity building interns who made the story map. I thought it was so interesting. Was it? I don't know. It was. I love finding like older nostalgic things, and it was really great to see kind of like your history, the historical findings that you guys discovered. Was that difficult? Was it like a task in itself to find some of this more like the founding of the developed program, or was it just like easily available?
I think for some of them, it was more difficult. Like with Indigenous Peoples Pilot, because it was so recent, it was pretty easy to find that information. I know one of the interns on our team, Hannah Wetzel, wrote a paper on just the history of the capacity building program. So like the research that she did for that paper really helped with creating the history for the tab or for the story map itself. Develop documents its history pretty well on the website as well. So it depending on the tab, some of it was more difficult to find, but since the work was divided up, it made it not too time consuming.
That's really interesting. I'd love to read that paper on the history of capacity building, because I, within this past week, have looked that up, and you get a lot of like history of NASA, but certainly curious about this specific branch. Yeah, we've got a hand from Sunita.
Yes, hello. Thank you for all the presentations. It was nice to hear them and see all the great things developed as. I was a developer a while ago, so it's good to see the current work. And I had a question for the Argentina agriculture team. So, I was just curious to know if they compared their tool to say the national statistics from Argentina, or even say the USDA foreign ag statistics, and just to see how their forecasting tool compared to those estimates.
Hi, Sunita. Thank you for your question. I was actually just about to respond to you in the chat, so thank you for all of your really interesting questions. In terms of comparison our NDVI forecast to other tools, we have not yet done so thoroughly, but that's definitely an area that we can explore. In addition to the other question you proposed in the chat as well, our tool can be modified to look at other regions as well, just by simply modifying the geometry in our script. So it can definitely be applied to other areas throughout the world. Thank you.
Okay, great. Yeah, thanks. It was interesting to see that. I do use some Google Earth engine, and my work is focused on Brazil. So, that's like, just move a bit further north, Thank you. I was just going to mention that if you needed any, pointers to where to find that information, at least in terms for USDA, I'd be happy, just free to reach out for that information.
Thank you so much. Yeah, that sounds great. Thank you.
Great. So I've got a question for the Florida team, the Transportation and Infrastructure Project. When you said our data spans 20 years, I still get shocked to remember that that's still in the 2000s. Do you think if you expanded that data farther, would it contribute more to the study, or do you think that so much change has happened in the time span itself that it would be kind of less relevant?
That's a great question, Alexa. Luckily, with the implementation of the Landsat series, we have data as far back as 1984, and it's consistent with all the data within our 20-year span. We capped it at 2000 only because that was really the range that dredging projects were being conducted from 2000 forward. Previous projects had been in the 70s, and unfortunately, we didn't have data for that. But as far as baselines, in everything that we've seen, the water parameters tend to stay pretty consistent. There aren't large fluctuations aside from sea surface temperature, which was something that we highlighted just kind of in a side, not necessarily due to direct influence, but just kind of global change. But beyond that, no, everything stayed pretty consistent. So I think adding time would just give a better look into how consistent it stays.
That's very interesting, and that's good to know. I'm sure, you know, your project partners were very happy with the work that y'all did.
Absolutely, thank you.
Okay, so at this point, we're about 4 minutes over, so if anybody has any questions, feel free to put them in the chat or raise your hand. If not, we're going to go ahead and wrap up the afternoon symposium. Thank you guys so much for coming and seeing all the wonderful projects that happen within Develop and through the sister programs. I appreciate your time for that, and I hope you guys really enjoyed the event.
By our kind of ending plenary wrap-up session. So please join us.
And for any Develop friends or alumni out there, we have the Develop Community Social immediately after the plenary, which will be in Wonder.
Yeah, I was just going to say the social. That's some time for.
Exactly. Thanks, everybody.
Thank you, guys.